Hello students, this is Mr. Allen, and today we are going to look at vectors in a plane. So we have already looked at parametric equations and polar coordinates. Now we're going to look at vectors. This is our third and final way to represent equations or functions. Our objective today is just to write the component form of a vector and perform basic vector operations. Many quantities in geometry and physics, such as area, volume, and temperature, can be characterized by a single real number that is scaled to the appropriate units of measure. These are called scalar quantities, and each number associated with them is called a scalar. Other quantities, such as force, velocity, acceleration, involve both magnitude and direction and cannot be characterized by a single number. A directed line segment is used to represent such quantities. The directed line segment PQ, that ray, has an initial point of P and a terminating point of Q. And its length or magnitude is denoted with these, it looks like a double absolute value symbol. The directed line segments that have the same length and the same direction are called equivalent. Now this is kind of one of the key things that you need to kind of keep in mind as we're doing these vector things. The set of all directed line segments that are equivalent in directed line segments PQ in a vector plane, and they're just denoted by bold V. In typeset material, vectors are usually denoted by lowercase boldface letters like U, V, and W. So vector U, vector V, vector W. And written by hand, we can go ahead and use this, looks like the ray notation that we learned in geometry. So let's look at example 1. It says, let the ray V, or the vector V, be represented by the directed line segment from 0, 0 to 3, 2, and let the directed line segment of U be from 1, 2 to 4, 4. Show that they are equivalent. So let's just draw a picture of them. So here is our first, oops, I'm sorry, that's the second one. Here's our first one. So we're going from 0, 0 to 3, 2. And then our second one here, so this would be V. This would be U, as you can see that we've written there. And we can see that these two particular rays are going in the exact same direction and that they have the exact same length or magnitude. Therefore, they are equivalent. The way you could do that to show their magnitudes are the same is just use the distance formula, which I'm sure you're familiar with. They both have square root of 13. They both have the slopes of 2/3. So this is the work. This is the work. So this is how you find the magnitude, and this is how you find the direction. So we have these directed line segments. Because the directed line segment PQ and RS have the same length and the same direction, they are called equivalent vectors. The directed line segment whose initial point is the origin is often the most convenient. So in other words, there's infinitely many ways we could represent vector V, but typically we just look at 0, 0, 3, 2. This represents V in its standard position, and a directed line segment whose initial point of the origin can be uniquely represented by the coordinates on the coordinate plane Q, V1, V2. So our definition, and this is the most important part of this particular lesson 9.6, is what we call the vector of a plane. If V is a vector in a plane whose initial point is the origin and its terminal point is V1, V2, then the component form of V is, and this is how we write it. Okay, so we use like these angle parentheses. The coordinate V1 and V2 are components of V, and the horizontal component is V2. I'm sorry, V1 is the horizontal component and V2 is the vertical component. And of course the zero vector is 0, 0. So this definition implies that two vectors U and V are equal if and only if U1 is equal to UV and V2 is equal to V2. By the way, we're talking about vectors here, not directed line segments. So the following procedure can be used to convert a directed line segment to its component form and vice versa. So you just do the following. You just subtract the x's, and then not subtract the x's. You're going to take P or Q1, that's this x, and then we're subtracting the x's, I did say that correctly, and then we're going to subtract the y's. So that's what you're doing. And then to find the magnitude, which is that double absolute value symbol, again, you're going to subtract the x's and then square, plus subtract the y's and then square. So there's our distance from it. So there we go. So if v is equal to v1, v2, and it can be represented by a directed line segment in the standard form where p is 0, 0, and q is v1, v2. Well, the length of v is also called the norm of v. If the magnitude of v is 1, we call it a unit vector. So here's our definition of vector addition and scalar multiplication. So if we need to find the sum of two vectors, it's very intuitive. You just add their horizontal components and their vertical components. Scalar multiplication is just like the distributive property, just multiply each of them by that component. If you multiply by the negative, then we just distribute the negative. And then, of course, subtraction. If we subtract, you're just going to just do like we do normally. Geometrically, the scalar multiple of a vector v and the scalar of c is the vector that absolute value of c times that of v. So in other words, if this is our vector v and we do 1/2 v, it's going to make its magnitude half. If we double it, it's going to double. If we make the negative, it flips the direction, etc. So those are just scalar multiples. So we can add. So if I add vector v to vector w, then we start here with u, we go up u, and then we go over v. So there's our addition. The u plus v is called the resultant vector, is the diagonal parallelogram. So you'll see here some examples of the resultant vectors. We can also do subtraction, which is basically addition of the opposite. So let's look at our second example here. So v is -2, 5, and w is 3, 4. So what's half of v? Well, we're just going to take half of v literally. So that's very simply -1 and 5/2. If we're going to subtract, we're just going to subtract. So we're going to do -2. So here we're doing, be careful, we're doing the w minus the v. So it's going to be 3 minus -2, and then 4 minus 5, which is going to give us 5, -1. And then, of course, we can do a combination of the two. So if we're going to do v plus 2w, you want to follow your order of operations and do 2 times the w first, and then add the v, and you'll get 4, 13. Here are some properties that you should keep in mind, like the commutative property, associative property, additive, inverse property for both addition of 0 and the opposite, and then the distributive properties apply. In some applications of vectors, it is useful to find the unit vector. The unit vector, again, we're just talking about, it's going to be in the same direction, but it's going to have a magnitude of 1. So the unit vector is simply the vector divided by its magnitude, which should make sense. And then there's some more information here. Notice that we can use sine and cosine in order to find the direction that it's going. And here's an example, but I'm going to go ahead and wind this up. Thank you for your attention.